Assalamualaikum and greetings to our lecturer and my fellow friends. We are group 4, consisting of Akmal, Ain, and me myself, Nafis. In this presentation, we will discuss the mathematical analysis of an IoT-based water quality monitoring system. The purpose of this assignment is to apply mathematical methods learned in engineering mathematics 2 to analyze the behavior of a water quality monitoring system. Our analysis consists of 3 tasks. The first task involves pollutant concentration analysis using an exponential decay model. Task 2 focuses on response analysis of a data acquisition module using differential equation. Finally, task 3 investigates a periodic sampling signal using Fourier series representation. Let us begin.
Task 1, pollutant concentration analysis. Given parameter based on our group, which is group 4, this task analyze how pollutant concentration change during a water treatment process. The concentration decreased from 135 mg per liter to 82 mg per liter in 5 hours. Our objective is to develop a mathematical model and determine when the concentration reach the target value of 25 mg per liter. To model the pollutant concentration, we assume that the rate of change of concentration is proportional to the current concentration. Therefore, we use the radioactive decay model represented by the differential equation, which is dC over dt equal to negative Kc, where C is the pollutant concentration and K is the decay constant. Next, we separate the variables by placing all concentration terms on one side and time terms on the other side. After integrating both sides, we obtain ln C equal to negative Kt plus A. Then, converting this into exponential form gives the general solutions. Using the initial concentrations, we determine the constant A, which is 135. Therefore, the concentration model becomes Ct equal to 135 exponent negative Kt. Next, we use the second data point where the concentration is 82 mg per liter after 5 hours. Taking the natural logarithm and solving for k, we obtain k equal to 0.0997. Hence, the concentration function describing the pollutant behavior is Ct equal to 135 exponent negative 0.0997t. This model can now be used to predict the concentration at any time during the treatment process. Exponential decay because the rate of pollutant removal is proportional to the amount of pollutant remaining in the reservoir. After obtaining the concentration model, the next objective is to determine the time required for the pollutant concentration to reach the target value of 25 mg per liter. To do this, we substitute the target concentration, which is 25 mg per liter, into the concentration function. Next, we rearrange the equation and apply the natural logarithm to both sides to isolate the variable t. Then we got the calculated time is approximately 16.91 hours. This result means that the water treatment process required approximately 16.9 hours to reduce the pollutant concentration from 135 mg per liter to the target concentration of 25 mg per liter. Therefore, engineers can use this model to estimate the treatment duration needed to achieve the desired water quality standard. This graph shows the concentration profile of the pollutant throughout the treatment process. As you can see, the curve becomes less steep as time increases, which means the rate of pollutant removal gradually decreases. This behavior is characteristic of an exponential decay process. Based on the concentration function and graph obtained, the pollutant concentration decreased exponentially as time increased. At the beginning of the treatment process, the concentration decreased rapidly because a larger amount of pollutant is available to be removed. As time progresses, the concentration becomes lower causing the rate of decrease to slow down gradually. The concentration continues to approach zero but never becomes negative, which is a characteristic of exponential decay. This behavior indicates that the water treatment process is effective in reducing pollutant concentration over time.
Assalamualaikum warahmatullahi wabarakatuh. So let's continue to the next part, which is task 2. As we can see, the parameters are given and the equation and the initial conditions, which is the original equation, and for the differential equation. So for solution for task question A, we need to find the equation for QT. So first, just simply substitute the parameters into the equation, and then substitute the differential into variables. And as you can see, the equation is in quadratic form, and just simply find the roots of the equation, and we get that the roots are unequal, two unequal roots, and from that we get the general solution form, which is given, which is shown, and apply initial conditions from the general solution to get value A and B. So for the first initial condition, we get the first equation, and then for the second initial condition, we need to differentiate the original equation first and rearrange the equation in order to get the second equation. After that, substitute the equation 1 into equation 2. We use substitution form to get value for B, and then we substitute B into the first equation to get value for A, and then substitute the value B and A into the general solution to find particular solution. So that's for question A. For question B, just simply put the T value into the equation, and we can get the value. For question C, the graph form is for the instantaneous beginning, it is flat because the differential value for the 0 is 0, so the gradient will be 0, but after that it will move downward but exponentially. That means it will never reach 0. The QT will never reach 0. And for the last question D, it is due to the high resistance, the charge will decay exponentially, as I mentioned earlier, and then the graph indicates overdamped response. Okay, that's all for task 2. Thank you.
For task 3, we are required to determine the Fourier series of the given function, which is ft equal to 7 minus t for the interval from 0 to 7. The first step is to identify whether the function is even, odd, or neither. After comparing the ft and f minus t, we found that the function is neither even nor odd. Therefore, we need to use the complete Fourier series formula that contains the constant term, cosine terms, and sine terms. Next, we calculate the Fourier coefficient starting with a0. After evaluating the integral, we obtain a0 equal to 7. Then, we'll calculate the cosine coefficient an using integration by parts. After simplifying the expression, we find that all cosine coefficients are 0. So, an equal to 0. This means the Fourier series will not contain any cosine terms. Next, we calculate the sine coefficient bn. Similar to the previous step, we apply integration by parts to evaluate the integral. After simplifying the result, we obtain the formula bn equal to 7 divided by n pi. Since an equal to 0, the Fourier series only consists of the constant term and the sine terms. Therefore, the final Fourier series is ft equal to 7 divided by 2 plus sum of 7 divided by n pi sine times 2n pi divided by 7 times t. This equation represents the original function as an infinite sum of sine waves. For the final part, we verify the Fourier series by using the first three terms of the expansion. The approximation is f3t equal to 7 divided by 2 plus 7 divided by pi times sine times 2 pi divided by t times t plus 7 divided by 2 pi sine times 4 pi divided by 7 times t. Next, we substitute t equal to 7 divided by 2 into the approximation. Since sin pi and sin 2 pi are both 0, the estimate value is 7 divided by 2. Finally, we compare this with the exact analytical value from the original function. The exact value is also 7 divided by 2. Therefore, the approximation is exactly the same as the analytical solution, giving 100% accuracy for this point. This verifies that our Fourier series solution is correct.
In conclusion, the mathematical techniques applied in this assignment successfully describe the behavior of the water quality monitoring system. Through task 1, we developed an exponential decay model to predict pollutant concentration and determine the time required to reach the target concentration. In task 2, we analyzed the response of the data equation module using differential equation and identify its response characteristics. In task 3, Fourier series was used to represent and approximate the periodic sampling signal accurately. Overall, this assignment demonstrates the importance of mathematical modeling in solving engineering problems and supporting the design and analysis of modern monitoring systems. Thank you for watching our presentations.